Hello friends, till now we discussed about what is a measuring instrument, what is an electronic measuring instrument, what is a voltmeter, what is an ammeter, what are the characteristics of an ideal voltmeter, what are the characteristics of an ideal ammeter, and what are the specifications of measuring instruments. The next topic is permanent magnet moving coil type instrument, that is in short called as PMMC instrument. The basic instrument that detects and measures the minute current is known as a galvanometer. Let us see how a galvanometer looks like. This is how a galvanometer looks like. These are different galvanometers fabricated by different companies. Basically, a galvanometer is used in lab applications, particularly for calibration of instruments. And PMMC instrument works on the principle of the galvanometer. Let us see what are the various parts of a suspension galvanometer. The various parts of a suspension galvanometer are coil of fine wire, as you can see here. A fine wire is wound on a iron core, a cylindrical iron core, and a permanent magnet. Here is the permanent magnet, and filament suspension. A filament in the sense a thin wire which is used for suspending the coil in the field of the magnetic field. Sorry, in the field of the magnet. Here the upper one and here the lower one. This is the filament of suspension, filament for suspension. And next, mirror. Here is the mirror. Mirror generally is used in measuring instruments to avoid parallax error. What is parallax error? Suppose when you are measuring a parameter and when an instrument is connected to measure that parameter, say for example current, then the current is measured as pointer deflection over a calibrated scale. Pointer deflection over a calibrated scale. That is, the current that is to be measured is allowed to flow through the coil of fine wire, which is placed in the magnetic field of the magnet. As a result, the coil tends to rotate. When the coil rotates, a pointer would be connected to the coil, and that pointer starts deflecting over a calibrated scale, and we can see the quantity being measured as a numerical value on the calibrated scale. But generally what happens is when you are noting down the reading of the meter, if you observe the pointer deflection exactly from the top, then you can see some reading. That means the pointer lying on a particular portion on the calibrated scale. When you look at the pointer deflection from either the left side in this direction or from the right side in this direction, sorry, from the right side in this direction or from the left side in this direction, then you will find a little variation in the position of the pointer over the calibrated scale. This is called as the error due to angle of vision, or in other words called as parallax error. If the angle of vision is exactly 90%, there won't be an error. If the angle of vision is not 90, either less than 90 or greater than 90, then definitely there will be some error in the measured reading. In order to overcome this difficulty, here an operator who is using the instrument to do some measurement, he would not be knowing he is making the mistake in noting down the reading. So to provide a standard for measurement, a mirror is placed on alongside the scale. A mirror is placed alongside the calibrated scale. So what we have to do is, while taking the reading, we have to see the pointer in such a way that the pointer and its image in the mirror coincide with each other. When the pointer and its image coincides with each other, that is the exact angle at which you have to take down the reading, at which you have to observe the reading. So the mirror is used to eliminate parallax error in the measurements. Next, of course, scale to move. There would be a calibrated scale, and that scale is used to give the visual display of the reading. Just like this, you can see here in this case. In the previous case, scale is not visible, but here you can see the scale clearly, and a pointer also is there, and a mirror placed here. Next, PMMC movement. This is about suspension galvanometer. The same principle is being employed in the PMMC instrument with a slight change in the construction. So, PMMC stands for Permanent Magnet Moving Coil. As the name indicates, it consists of a permanent magnet and it consists of a moving coil. Here, this is the construction. This is a diagram showing the construction of a permanent magnet moving coil type instrument or movement. You can see here, it mainly consists of a coil to produce deflection. Here is the coil used to produce deflection, and a permanent magnet to give the magnetic field. Here, this is a horseshoe type permanent magnet which is used to produce the magnetic field, and a pointer. Here is the pointer. Pointer is used to indicate the quantity being measured on a calibrated scale. Then control springs. Here one control spring is there, and at the bottom of the coil also we will find another control spring. And then control weight. Control weight is placed on the second side of the pointer. As you can see here, the length of the pointer on one side is more compared with the length of the pointer on the back side. This is the end portion of the pointer. Now what happens, because of this variation in length on two sides of the pointer is actually hinged here or connected here. So when the pointer starts deflecting because of its weight, here the weight of the pointer would be more compared with this portion when additional weight is not placed on the second side. So because of the additional weight, the pointer tends to bend it down when control weight is not placed on the other side. So in order to maintain the balance of weights on two sides of the uh, pointer, a control weight is placed. Next is pole shoe. Here are the pole shoes. Pole shoes that are provided here with curved faces. I'll tell why the curved faces are used. Next, zero position control. Here there is a zero position control. What is the purpose of zero position control? Suppose, let us assume that no current is flowing through this instrument, and for some reason the pointer is not showing zero on the calibrated scale. It is lying on some place on the calibrated scale where the meter reading is more than zero. We know that there is no current applied, but still the pointer is not lying down at zero position of the calibrated scale. In such case, as an initial correction before taking the instrument for measurement, we can set the pointer to move on to zero position of the calibrated scale. For that purpose, this zero position control is used. Here, a simple screw will be there. By adjusting the screw using a screwdriver, you can make the pointer to move back onto zero position. Now, this is another view of the PMMC instrument. Same parts, but here they are more clearly visible, as you can see. Coil for, coil to give deflection. That is, here is the coil to give deflection, and permanent magnet to produce magnetic field. Here is the permanent magnet, and pointer and scale. Here is the pointers. Scale, of course, is not shown here. And control spring. Control springs are clearly visible here. One is upper control spring, the other one is lower control spring. Here, what is the purpose of control spring? Suppose, let us assume that uh, the meter is connected to a circuit, and the circuit is switched on all of a sudden. When the circuit is in switched off condition, the meter is connected to the circuit and the circuit is turned on. Then in that case, the pointer actually, initially it was lying down at 0. When the circuit is switched on, that means some current starts flowing through the pointer. The pointer has to shift abruptly from 0 position to the position indicating the current flowing through, to a specific position indicating the current flowing through the meter. So because of that abrupt movement from 0 to the specific position indicating the amount of current, there is a possibility that over a number of usages, the mounting of this coil, movable coil assembly may get disturbed. The mounting of the movable coil assembly may get disturbed because of the abrupt movement of the pointer from 0 to the specific position multiple times. That means when you are using in multiple times, just in this fashion, that is connected with no power and switched on, all of a sudden the pointer has to make abrupt movement to show the current flowing through that. So in such cases, what happens then, as I told, the assembly of the mounting assembly of the movable coil gets disturbed. In order to prevent that disturbing of the movable coil assembly, two control springs are placed here. One is on the top and one is at the bottom. And current flows through this coil through these control springs. Starts from here, either flows through the coil and comes out like this, or enters into the coil, moves in this direction, comes out from the upper control spring. So using this control spring, what happens when the circuit in which the instrument is placed is switched on abruptly, the pointer movement will not be abrupt because of this control spring. Control spring will possess some tension. So instead of, it will not allow the pointer to move freely. Instead, it makes the pointer to move slowly from 0 position to the specific position indicating the exact amount of current on the calibrated scale. So by using this control springs, we are preventing the abrupt movement of pointer over the calibrated scale, thereby avoiding the disturbance to the mounting assembly of the movable coil. Right. Next, as I told, control weight, because the pointer is hinged almost at 3/4 length of 3/4 of its length. 1/4 of its length is on one side and 3/4 of length is on the other side. Because of the imbalance in weight, the pointer may bend down while moving over a number of times. So in order to prevent bending down of the pointer, the control weight is placed. And next is pole shoe. Here is the pole shoe. Pole shoe is used with soft iron, with curved faces. And of course, 0 position control. Here it is clearly visible. By adjusting this screw, the pointer can be brought back to 0 position. Another view of the same PMMC movement construction. To have a clear idea when compared with the previous two diagrams. Here is the magnet and here is the soft iron cylinder over which a movable coil is placed. The soft iron cylinder is used as core for the movable coil, That means the movable coil is wound on the soft iron core, and here is the pointer and the two control springs, upper and lower control springs. And this is the diagram which is meant for drawing in the examinations. You can draw this diagram and explain the construction and working of the PMMC movement. It will be somewhat simpler to draw in the examinations. It will minimize the time for drawing. So here is uh, the basically core, soft iron cylinder used as core. Then next coil former on which the coil is wound. Finally movable coil, the upper end, and magnet, permanent magnet, North Pole and South Pole, pointer, and a mirror and scale is placed here, balancing weight here, control spring, and pivot and jewel bearing. We will discuss about in detail a little later. This pivot and jewel bearing is the one which is responsible for the stable working. That is, the movable coil mounting is done using this pivot and jewel bearing. That means a groove is done in the jewel, and a pivot which is connected to the movable coil assembly. Two pivots will be there connected to the movable coil assembly, one at the top and the one at the bottom. Those are placed in the groove of the jewel, and when current is flowing, then this pivot will be freely moving in the groove of the jewel, so that the pointer movement, because of the current flowing through the coil, would not be disturbed. So this is about the construction of a basic PMMC movement. Working of the basic PMMC movement we will see later.